Hey everybody, we are going to look at all the gas laws and I want to review them and practice them with you. I know you watched a couple videos that broke them down, but I just figured it would be helpful if you had a one-stop shop so you have everything in one place. So I sent you an all gas law review and practice document inside your OneNote, so you should have it there. I would recommend filling this out as I'm talking, so that way it'll make a little bit more sense if you were a little fuzzy after the videos you had just watched. So at the top here, there's a chart, and it has all of the gas laws that you learned about in the videos. So start with the top here, the combined gas law. Okay, so that's working with pressure, volume, and temperature. However, in order for you to be able to manipulate those variables, something has to stay the same. So constant, something that's staying the same, is the amount of gas. Okay, so the amount of gas is what's staying the same here, and that's going to be your N value. And you know that that's moles. Okay, the variables that are changing, well, those are the things that are in the equation. So pressure is changing, volume is changing, temperature is changing. Okay, next one, Boyle's law. Okay, the constants. Well, the constants, again, are the things that stay the same. And if you check out the equation, you should notice that one of the variables is missing when you compare it to the combined gas law. Well, the thing that's missing is the thing that's staying the same, along with the amount of gas. So the constants for Boyle's law are the amount of gas, which is the N value, and temperature. You're not changing that. Things that are changing are pressure and volume. And just to remind you, there's an inverse relationship between pressure and volume. So if you increase one, the other one is going to go down. And if you decrease one, the other one is going to go up. So I'm just going to write that off to the side here. This is an inverse relationship. Okay. A quick little way I like to remember that is Boyle is VIP. Okay. So Boyle is V for volume, inverse for I, and then P for pressure. Boyle is VIP. So just something that's stuck with me since high school. Charles's law is the next one. And if you, again, look back up to the combined gas law, you can see that you're missing pressure here. So if you were remembering what I said about Boyle's law, pressure is going to be a constant along with the amount of gas. So N and P this time. And the things that are changing are volume and temperature. Okay. Charles's law is a direct relationship. So if you increase one thing, the other one is also going to go up. And a quick way to remember Charles's law is Charles watches DirecTV. So there's a direct relationship between T and V. So again, something that's stuck with me since high school. Gay-Lussac's law. Check out the equation. We're missing volume. That means it's a constant here. So N and V. The things that are changing are P and T. This guy is a direct relationship. I don't have a fancy saying for this one, unfortunately. Okay. So if we check out number one, the easiest way to figure out what's going on is to label your problem and write your equation. So what I always like to do is I like to write the entire combined gas law formula off to the side there and then cross off the one that I don't need. So I'll show you what I mean by that. So number one here, it says a gas occupies a volume of 2.45 liters at a pressure of 1.03 atmospheres. What volume will the gas occupy as the pressure changes to 0.98 atmospheres? So a couple things. You want to make sure you're working with consistent units. So for example, if they gave you one pressure in atmospheres and something in another one in millimeters of mercury, or kilopascals, whatever, you have to make sure you're working with consistent units. Same with volume units. You have to make sure you have the same thing. So I like to write my combined gas law over here. So P1 V1 over T1 is equal to P2 V2 over T2. And then I'm going to check out my question here and see what they're giving me. So they told me that it occupies a volume at 2.45 liters. Well, that's the first volume they gave me, so that's going to be V1. And the pressure is 1.03 atmospheres. Well, that's a P1. What volume? Okay, well, they're asking me about volume, so that's going to be a V2. Will the gas occupy as the pressure changes to 0.98 atmospheres? Well, that's a P2. They did not mention temperature anywhere, so that must mean I don't need it. So then, if you were to check back up here, you're working with Boyle's law, okay? I don't necessarily care that you know that it's Boyle's law, Charles' law, Gay-Lussac's law, like specifically by name, but I need you to know that if you're working with pressure and volume, that it's VIP and Boyle's VIP. So if it helps you to remember Boyle is VIP, that's fine. If you just want to remember VIP, that's fine too. I don't necessarily need you to know specifically that Boyle is the guy. Okay, so now we just have to solve our problem here. So this is what our end formula is going to consist of, this P1, V1, P2, V2. All right, so P1 here is 1.03 atmospheres. V1 is 2.45 liters. And then my P2 is 0.98 atmospheres. And then V2 is what I am looking for. So I'm just going to highlight that so I don't lose it. You're going to want to clean up the left side of that equation. So in your calculator, you're going to multiply 1.03 times 2.45. And when you do that, you will get 2.52 ATM times L. You're going to want to make sure that you pull down your units. And then you want to rewrite the right-hand side of that equation. Okay, so 0.98 ATM times that V2. Again, I'm going to highlight it so I don't lose it. How do you get V2 by itself? Well, you got to divide each side by that 0.98 atmospheres. So divide each side by 0.98 atmospheres. Okay, and you're going to lose some stuff over here, so this cancels. I'm going to lose atmospheres here, and when you divide that in your calculator, you're going to get 2.57 liters is equal to V2, and that's your final answer. Okay, let's take a look at this next one. So it says, a gas sample at a temperature of 83 degrees Celsius occupies a volume of 1,400 milliliters. At what temperature would it occupy 1,200 milliliters? You should see a huge problem. Celsius. Nobody likes Celsius. We need to get it to Kelvin. And remember, in order to go from Celsius to Kelvin, you have to add 273. So when you do that, you will get that it is 356 Kelvin in your calculator. Okay. So now let's write our formula. P1 V1 over T1 equals P2 V2 over T2. Now let's read our problem again. So a gas sample at a temperature of, well, this is going to be T1, occupies a volume of 1,400 milliliters. Well, that's a V1. At what temperature, T2, would it occupy 1,200 milliliters? That's V2. No mention of pressure, so that means I don't even need it. And if you look up here, that's Charles's law. Again, I don't care if you know that it's Charles's law. I just need you to know that it is direct TV. There's a direct relationship going on here. So your equation is going to be V1 over T1 equals V2 over T2, just like that. Well, now let's just sub in all of the things that they gave us. So V1 here was 1,400 milliliters. T1, 356 Kelvin, equals V2, which is 1,200 milliliters, over T2. And T2 is what I'm looking for. Now, here's where people do some goofy things with math. Please don't do the goofy things. Just cross multiply. It's the easiest way to solve this thing. So what you're going to cross multiply are these two things and these two things. Okay? Green stuff is going to go on the left. So I'll write it over here. 1,400 milliliters times my T2 equals, and then in my calculator I multiply 1,200 times 356 Kelvin. And when I do that, I'm going to get 427,200 milliliters times Kelvin. And again, I'm going to highlight that T2 to make it very obvious what I'm looking for. That's the easiest way. Some people multiply by reciprocals and they don't cancel correctly. The easiest way is to cross multiply because you can simplify it and just make it into a linear equation that you can solve. So how do I get T2 by itself? Well, it's business as usual. I just have to divide each side. 1,400 milliliters. I'm canceling some stuff now. This cancels. My milliliters cancel. And when I take 427,200 and I divide by 1,400 milliliters, I'm going to get 305.14 Kelvin. So T2 equals 305.14 Kelvin. It just makes it much simpler if you do it that way. Okay? I hope we're doing okay so far. If you have questions, you can always email me. Number 3. The pressure in an automobile tire is 980 millimeters of mercury at a temperature of 27 degrees Celsius. At the end of a journey on a hot day, sunny day, the pressure has risen to 2.1 atmospheres. What is the temperature of the air in the tire? Well, a couple things here. This one's a bit of a mess. Why? Well, first thing, they gave us Celsius, and they gave us 2 different pressure units. It doesn't matter what you convert to. They just have to be the same. So if you like atmospheres, make it atmospheres. If you like millimeters mercury, make it that. But either way, they have to be the same unit. Okay? So, first thing, I'm always going to write my combined gas law. So P1, B1, T1, P2, B2, T2. Okay? So, let's figure out what they gave us. They gave us a pressure, they gave us a temperature, and they gave us another pressure, and they gave us another temperature. No mention of volume. So that means I don't even need it over here. And so my equation is P over T, and that's Gay-Lussac's law. Okay, so let's do a little bit of converting really quick. I'm just going to convert from millimeters of mercury to atmospheres because that's the first thing I saw. So 980 millimeters of mercury over nothing. 1 atmosphere is equal to 760 millimeters of mercury. So the way to get rid of a variable you don't want is to make sure it's in the denominator in your T chart. Okay, and then when you multiply across, these things are going to cancel. So in your calculator, all you're going to do is take 980 divided by 760, and you're going to get 1.29 atmospheres. So the P1 that you're working with is not actually 980. So cross that off so you don't get goofed up. 27 degrees Celsius. Nobody likes Celsius. And when you add 273 to that, you're going to get 300 Kelvin. Okay, now we're in business. Now we can solve this problem. So, first pressure is 1.29 atm over my first temperature, which is 300 Kelvin. And my second pressure is 2.1 atmospheres over my second temperature, which is T2. And I'm going to highlight that so I don't lose it. This should look strikingly similar to number 2. Why? Well, we have to cross multiply. It's the easiest way to get the answer correct. So again, I'm going to multiply green stuff and my blue stuff, and I'll put my green stuff on the left-hand side. So I'm going to have 1.29 atmospheres times T2. And again, I'm going to highlight it so I don't lose it. Equal to, you take 300 and you multiply it by 2.1 in your calculator, you're going to get 630, and don't forget your units, 630 ATM, atmospheres, times Kelvin. I got to get T2 by itself, so that means I have to divide each side by 1.29 atmospheres. I'm going to lose some stuff, so this cancels here. This unit cancels. And I'm going to get, when I divide these numbers in my calculator, I'm going to get 488.37 Kelvin. That's my final answer there. Okay. Last one here. A gas collected at 17 degrees Celsius and 380 millimeters of mercury has a volume of 12.5 liters. Find its volume at 37 degrees Celsius and 0.66 atmospheres. Again, bit of a hot mess. They gave us Celsius, and they gave us different pressure units. So I don't forget, I'm going to write my combined gas law formula over here. P1, V1, T1 equals P2, V2 over T2. Okay, and I'm going to tackle all this mess. 17, when you add 273, cross that off while I'm at it, you're going to get 290 Kelvin. And when you have 37 degrees and you add 273, you're going to get 310 Kelvin. Since 380 was the first pressure I hit, I'll just convert that to atmospheres. And again, 1 atmosphere is equal to 760 millimeters of mercury. We'll lose some units. And then 380 divided by 760 in your calculator is going to get you 0.5 atmospheres. Okay. So I'm going to cross this off so I don't confuse myself while I'm writing it down. Now let's label our stuff. So this is a T1, this is a P1, and this is a V1. Then it says find its volume. Well, it's V2 at 310 Kelvin. That's a T2. And this is a P2. So it looks like they want us to use the combined gas all this time because they've mentioned all of the variables and they gave us 2 of them, of everything, except for volume, the V2, which is what we got to find. So let's just sub everything in. P1, I converted that to atmospheres. So I'll just start writing down here. P1 is 0.5 atmospheres. My V1, 12.5 liters, over my T1, which I converted to Kelvin and got 290, equals P2, which is 0.66 ATM. V2 is what I'm solving for, over T2, which is 310 Kelvin. I'm going to highlight that V2 just to make it obvious to myself what I'm looking for. Anytime you have numerators and denominators, guys, just cross multiply. It's just a couple more numbers, that's all. So we're going to cross multiply all this stuff. We're going to cross multiply all this stuff. So green stuff goes on the left. In your calculator, you should multiply 290 by 0.66. And when you do that, you will get 191.4 ATM times K. And you still can't forget to pull that V2 down because that's multiplied too. And then in your calculator for the blue stuff, you should multiply 0.5 times 12.5 times 310. When you do that, you will get 1,937.5. And I'm going to write all my units. ATM times liters times Kelvin. This should look familiar. How do I get V2 by itself? I just have to divide each side by 191.4. ATM times K. 191.4 ATM times K. I'm going to cancel this stuff here. I'm going to cancel these units. And then my calculator, when I take 1,937.5 divided by 191.4, I get that my V2 equals 10.12 liters. It might seem kind of silly or redundant to keep writing the units over and over and over, but you should notice that you're ending up with the unit that you need. It's a way to check yourself before you wreck yourself. And what I mean by that is if you look, you have V2 on the left there. Look what unit you were left with over here. That's what you want. And it happened every single time. Even if you look up here, T2, when you canceled all your units, what were you left with? Kelvins. Look over here. You canceled all your units. What were you left with? Kelvins. Here, you're looking for volume. What units were you left with? Oops, liters. Okay, so I know I say it in class and I know I harp on you about it, but the reason why is it's a great way to check yourself. If you have questions, shoot me an email.